Thank you. All right. How was the career fair last week? Is it good? Anybody got any job? Wish it was that easy, right? Yeah. I want to tell you something about the jobs, just to make you feel optimistic. Almost, I'll say 99% of our students get jobs before they graduate, okay? Talking about masters, bachelors, and PhD students. And we have a lot of people that join generally really good companies as either software engineers, data scientists, whatever other UI engineer, all our students generally, I'll say most of them, they get jobs. So you don't have to worry about that. And this class, every single person who took this class okay, is anybody from past offerings of this class right here? You can talk without feeling somebody will object. All right, everybody in this class get a job, okay? A semester, for some reason, a semester after that right away. Especially if people that are interested in whatever data science, big data kind of jobs, right? So the career fair will definitely help if you have some strategies to meet people and networking and all these kind of things. And we hold different career fairs across the year, so you have, even if you didn't attend this one, you have other chances, right? But what matters the most is your skills, right? And the concepts you learn during your degree. So I'm just saying. So yeah. So all people have taken this class before, got really good jobs, right? So if this is what some people don't. I mean, I just realized something. I was talking to a student like a couple of months ago, and I noticed they're not interested in jobs. So I'm just like, why you're taking education, right? So there is a shift in interest. Some people don't want to have a job. Some people actually want to have their own business. And this is really interesting, and I like it. So they say like, no, I don't want to work for Amazon or Facebook, or it's like, some people think this is not their thing, right? And they want to have their own business. And we have actually students also. And I'm not sure, all of you are from SITSI or part of SITSI, or some of you are from maybe electrical, some of you are from Polytechnic, few, or like software engineering. But we have in SITSI, we have several student groups that started companies, right? So, and they raised funds and things are going well. So even if this is a thing you want to consider, we have a good history, and actually ASU helps with that. So, so I usually tell like my students, so talking about my students, I'm saying like PhD students, like, you know, when you're advising PhD students and you want them to succeed very badly, you want them to succeed in any way, but you have like a priority list. Most professors, they have number one thing they want for their PhD students is to be professors, right? So that's their ultimate job, like dream for their students in a good school. So, but I always tell my students, like, what's better than that if you build the next Google, right? Why is that? It's going to give me money, right? That's a good thing. All right. So anyway, I hope you enjoy the career fair. So those of you who have attended, it's okay that you did that. It's eventually this is for the whole degree that you're doing and all education. Most of you want to get a job eventually, so there's nothing bad about this. So don't feel bad if you didn't attend the class last time. Anyway, so where were we last time? Anybody can remember the last scene of last time? Yeah, what we have seen on the screen the last time, the last thing we've seen.
Analyzing the query.
Analyzing the query, I got like a Postgres, whatever terminal on the screen, and we played with the queries. We had a users database, and we did a simple query, and we did a filter in the query, and did a join, and then many of you explored the explain analyze SQL command in Postgres. I hope some of you have tried it after that last lecture, so to see. So this is basically to help you understand how Postgres actually optimized the query, what kind of plan it actually ran. Okay, and then I showed you a little bit of statistics. So what Postgres does in the explain analyze, it shows you, it runs the query, it optimizes the query, it runs it. It gets you the actual time the query took to run and the estimated time. And in many cases, both of them match. And when the query gets a little bit complex, so optimization is not very accurate. So, I mean, they do not match the estimated time compared to the optimized query and compared to the actual time the query ran. So they do not match, but they're close. Like Postgres is actually very good at doing optimization. So what kind of statistics we talked about last time? Or what kind of statistics major database systems use to optimize a query? Like I remember the gentleman in the back mentioned last time the size of the table, how many tuples we have. And this will tell us if we're doing a scan, if we're scanning the whole table, how many pages we're reading. And this will give us the I/O cost, right? Simple as this. But what if I'm doing a scan, or I'm having an index scan, like we've seen last time, which is I have an index, and instead of accessing the real pages and scanning the whole table, I'm getting the values through the index. How much is the cost of the index, of getting the data through that index scan operation? There are things you need to learn about the estimated cardinality of this kind of operation that runs to get the size of the intermediate results. What I mean by intermediate results is the data that each operator gets and pass it to the next operator. So if you have, let's assume you're having selection. The selection selects from the user's table, select one user. But the condition actually in the word clause does not say that it's only one user. It says select all users where age is 18 or less. And if there's only one user in the million users in the system that satisfy this condition, if I don't know the selectivity of this condition, which is age less than or equal 18, the optimizer will assume that you'll have to, the results return is, maybe it will assume uniform distribution of the age, okay? And then it will say, okay, if we have a million users and you have 5 age ranges, so I will million over 5, so the return tuples will be this number, okay? Which is million over 5, what is it? Divided by 5? Come on, guys, this is not even like, yeah.
100,000.
Okay, 200,000. So 200,000 tuples. While, in fact, you have only one tuple that satisfies this constraint. So getting this tuple, you need to have some kind of statistics not only about the size of the table, the number of tuples in the database. These statistics are still necessary, but you need to get more. Okay? So, for example, you need to get, how can we solve this problem? Like, how can we get better statistics that help us with this kind of optimization? Please. Keep a histogram data. So we have a histogram, which is the distribution of the data, pretty much. So if you have kind of the distribution of the data, or a histogram that represents for each value, age value, we have age, different bins of the age range, and you show how many of the tuples represented by this attribute. And you have this for every attribute. You need to also, way more basic than this, is you need to learn how many values are actually in this attribute. Like, if I have an attribute like gender, how many values can be in there? 3. Yeah, maybe. Yeah. It's limited, right? So 2 or 3. So how can you, the database doesn't know that unless you give them the statistics. So you need to know the values that this attribute represents. Not only this, let's assume that the attribute, the domain or the type that you're defining has 3 attributes. Oh, sorry, has 1,000 values. But the database at hand, the table has only 10 of these attributes values. So you need also to know that. The query optimizer needs to learn all of this. So I'm going to give you an idea of what the basic statistics that the query optimizer stores in the catalog, or the database stores in the catalog, and these statistics can be used by the optimizer later. So you have a relation, and relation has different attributes, like A1 to AN. These are the columns in the table. And they're represented by different fragments, the same relation. So the length of each attribute is basically the size of this attribute, okay? And then the number of distinct values for each attribute is called the cardinality of this attribute, all right? So the maximum minimum values also of the domain of the attribute are represented by min AI and max AI. And then the cardinalities of each domain is the cardinality of each domain of this attribute, which is how many values are in the domain of this attribute. So the first one, how is this different? The first cardinality is different than the second this cardinality is the fact that this one calculate the number of distinct values of this attribute in the fragment, okay? While this one calculates the number of distinct values of the domain of this attribute in general, okay? So in other words, the cardinality of the domain of an attribute that is an integer is if the attribute is an integer type. Okay, the attribute is a gender type. What is the cardinality of the domain of this attribute? 3, okay? Or 2, however it's defined, I mean in the database. So in an integer, it's like the possible number of integers. That's the domain of an integer. And then the cardinality of each fragment, or of a relation in general, is the number of tuples in that relation. Okay? And most importantly, we do all of this to calculate the selectivity factor. Selectivity factor means if you have an operation applied on a relation or a fragment or a data source, what is the percentage of the original data that is returned by this operation? For instance, if we're doing a join between R and S, the selectivity factor of this join is actually the number of tuples returned by the join divided by the Cartesian product result, the number of tuples resulted from the Cartesian product, which is the cardinality of R, cardinality of S, multiplied together. Because this is the worst case join. This is the maximum join result, or the join can return. And this one is the real return number of tuples from the join. Selectivity factor is basically, you have an operation, a number of tuples in, number of tuples out. What is this proportion? Think of a selection. If you have a simpler than that, selection. So the table, and you're selecting directly from a table. Selecting from this table, if the table again has 1,000,000 tuples, and the return result is 1, the return tuple from the selection is 1, so the selectivity factor is 1 over 1,000,000. If it's 10, 10 over 1,000,000. It can get complex again with join. It can get complex even if you have multiple levels on top of each other. So it is the job of the query optimizer to calculate the selectivity factor of each single step in the query tree that we've seen. And using the selectivity factor, you can actually calculate the size of the intermediate results, and hence you can figure out the cost of the plan. Like accumulate all of this in the cost model and get the cost of the query tree. And if you have 10 of them, you compare them and you get the minimal cost across all of them. So calculating the selectivity factor is the issue. So how would I know the selectivity? So this one is theoretically, yeah, I mean, we understand it. So I told you about the selection. So one tuple returned and you have the size of the table is 1,000,000. But how would you know that there is only one tuple returned? You need to use the statistics we talked about. All right? So let's go through this exercise. So you guys, let's assume you have a relation R, okay? And the size of R is the cardinality of R times the length of R. The length of R is the size of the tuple, okay? And then the cardinality of R is the length, the number of tuples you have. The cardinality of the selection of R is the selectivity factor of this condition, you apply in the selection, multiplied by the cardinality of R. Which means if the selectivity factor is, again, 1 over 1,000,000 as we mentioned, and you have 1,000,000 tuples, so 1 over 1,000,000 times 1,000,000, so the returned, the size of the result will be 1 tuple, right? And that's the cardinality of this operation. That's what it means. So the cardinality of the result of an operation applied to a fragment or to a relation is the selectivity factor of the selection condition, which is F here, times the cardinality of the original relation. Does it make sense? So this is just a mathematical formula to represent the example we talked about. Now, I want to know if I have a selectivity factor and the attribute is A equal a value. That's the condition you have. You have a selection on a relation R, and the selection in the where clause in this selection, you have a condition on an attribute A, which is a column in this table, but you have an equality condition here. So you want to find all tuples such that A equal a specific value. This value can be anything. And I want to figure out the same if the condition was A larger than a value, and the same if A is less than a specific value. Again, so A is a generic, could be any attribute. This value is not like it would be plugged in for the optimizer. But how can the optimizer automatically calculate that? Assuming that the data is uniformly distributed. So again, these are the kind of statistics we talked about. I'm just bringing it here for you to summarize. I want you to tell me, some of you, what is the selectivity factor of A equals value? Just wild guess, using the statistics we have. Please.
1 over max AI minus unit.
1 over max AI minus
So 1 over the region.
1 over, why is that? Explain, I want to understand why you think that.
If we're going to go uniform distribution, then since every step along the way has its own equal value, and we're going to divide the entire range equally. So max AI would be just 1 over the range.
You're actually very close. I mean, you have a point, and it's very close, and it can be that way, but it's not as generic as the values that you have. It's, as you said, if it's uniformly distributed, you have one value, so it's 1 over, and then the cardinality of the domain in the relation, right? Instead of just the whole range of values. Okay. Why is so? In other words, so you have an attribute, and the attribute here is A. Okay. The cardinality of the projection of A on the relation is actually the total number of distinct values for A in that relation. And if you assume uniform distribution, so it will be 1 over that. Okay? You guys understand what we're talking about here. So again, I didn't have any information. I just have this simple statistic, and I could calculate as an optimizer for any kind of values, for any kind of attributes. I can calculate the selectivity factor of this condition. Please.
You say A was like numbers that integers or something. They were continuous, only like 1 through 10. What is it to be right there? The max minus the min. Because then you're choosing 1 through 10. But are you saying it's the cardinality because maybe you don't have a 5 or a 7?
The cardinality is basically because these are the actual distinct values of this attribute in here. Yeah, you're right. So you don't know.
You don't know if it's continuous.
Yeah.
Makes sense.
So, and if it's uniformly distributed, also makes sense because it's 1 over. If it's not uniformly distributed, you don't know, right? Maybe you need more information in that case. But with this assumption, this is valid, and it's going to work pretty well. Okay, so what about the second condition? Go with the same thinking. What do you guys think the selectivity factor of A larger than a value? Anyone? Please.
The number of values that are greater than A.
Like how in an equation? Give me an equation.
I guess I was thinking it would be max minus A, but that wouldn't work with C.
Max minus A to
Say minus A, but that would
minus A. What is A? You mean the value that is in A?
value, but that kind of falls the same.
No. Why is that? Okay, here's the thing. Think of again, this is a ratio we're calculating. The upper part in the division doesn't need to be exact, as well as the bottom part of the division also doesn't need to be exact. But the ratio is the one that matters. It's one that makes sense. So you were talking, again, you said max minus value divided by, so you understand that max minus value will not give you the actually the real difference in the table. But to bring this ratio, to make this ratio make sense, assuming also again uniform distribution, so you divide this by max minus min, right? Yeah. Makes sense. So we calculated selectivity factor for this greater than a value using max minus the value over max minus min. What about the selectivity factor of the less than? Value minus min over max minus min. So again, given this simple assumption, given these very simple statistics, the optimizer can actually calculate the selectivity factor of a selection. All right, so what about if I have multiple conditions? So I have A equal value and another condition also that I want satisfy in the selection. What shall I do in this case? Like if I want the selectivity factor of a condition applied to A and another condition applied to another attribute. Okay? And the same conditions here, but I have AI and AJ. And I want the selectivity factor of the selection operator for AI, the condition applied to AI, and AF. It's as if in the SQL query you have select from where attribute 1 equal a value and attribute 2 is larger than a value. If I have this condition, how can I calculate the selectivity factor for that? So sorry, please.
Multiply the two selectivity factors.
Why is that?
Think of it in terms of probability. You find the probability of having one thing, and you want the probability of having the other thing conditioned upon it.
Perfect. Yeah, exactly. It's a perfect answer. Actually, think of it, it is actually probability. If you think about from a probability theory kind of thing, or from set theory, right? So you have two sets, and you want to find the intersection between the two sets, right? It's an and. So this is how you calculate the selectivity factor for both. You multiply the two probabilities together. Okay, what if you have two conditions, one on AI and AJ, and instead of it's an and, it's an or. So how can you calculate the selectivity factor? Probability theory again, how you do that? So, please.
We add them and reduce the common part.
So you add the selectivity factor of the first one,
And the second
plus the second one, minus,
minus the combination of the
which is the intersection, like the two multiplied together, right? Right? So, very easy. So again, if you have a more complex query, that you have multiple conditions in the same word clause, you can use very simple math here to calculate the selectivity factor for any kind of condition you have in the word clause. Does it make sense? So this is how the optimizer works. Theoretically, if the data is uniformly distributed. All right, please.
I didn't understand how the maximum and minimum value of an attribute is related to the number of tuples.
It's not. Okay, that's why. Okay, the ratio makes sense. Each part, like maximum minus minimum, does not return any number that makes sense. Okay, but the ratio of it, like of maximum minus value over maximum minus minimum, it actually makes sense because you divide two things that are similar to each other, so you can get the same ratio as if you get the real cardinality for the bottom part and the real cardinality for the results. All right, so example. Let's assume you have a table that has an attribute, and the attribute has values 1, 2, 3, 4 till 10. Okay? And the maximum, the minimum is 1, the maximum is 10. Okay? And the selectivity that you want to calculate is for this attribute larger than 5. if you do max A 10 minus 5 over 10 minus 1, what will this give you?
But here the data is like uniformly distributed.
Yeah, it is uniformly, the assumption is that the data is uniformly distributed. Okay? So it will give you the ratio you're looking for. Okay? Uniformly distributed does not mean that each tuple is represented by 1, but it seems that things are uniformly distributed. Please.
I think that the select factor A equals value should be 1 over max minus min, because there may be multiple values, multiple tuples.
Yeah, that's the first thing we talked about. The idea with A equals a value, you can actually get a more accurate result in that sense because you have the real values represented in that sense. By this, the real distinct values you have in this table.
Yeah.
Okay? The other one is a range. You don't know the distinct values in each separate range. This is why we've done this max minus min. This one, you don't need to do that. This one actually is the most accurate across all of them in case of uniform distribution. Because you have the exact number of distinct values for this attribute in the table. So again, coming back to the example we're talking about, you have 1 to 10 and you have 10 distinct values. So if I'm looking for a specific value, you're pretty sure it's 1 over 10. Okay?
So
let's assume that the domain, the domain is 1 to 10 for this attribute, but you have the values in the table are only 1 to 5. Okay? So in this case, the cardinality, the selectivity factor will be 1 over 5 as compared to 1 over 10. So 1 over 10 in this case, which is max minus min, will not make sense. It will make sense if we have 1 over 5 because 5 is cardinality of the attribute in the relation.
it's evenly distributed.
What is that?
You said it's evenly distributed.
Yes, but it's only 5 values in the domain that are evenly distributed, that are uniformly distributed, right? Please.
So query optimizer assumes that this is normally distributed.
That's if the data is uniformly distributed. I'm showing you this is the easy way to think of. But no, this is just a simplified way to look at the problem. The problem is definitely more complex than that in other kind of distributions. All right? Okay, so cardinality of the projection. Cardinality is equal, if you have a projection operator, projection means you're selecting the attribute, like only one attribute in the table. So the cardinality of this is actually the cardinality of the relation, right? The number of tuples of the relation, right? So what if we have a Cartesian product? What is the cardinality of that?
Cardinality of R into cardinality of S.
Cardinality of R into cardinality of S. Why is that?
Because in the Cartesian product we are taking one tuple of the R and combining it with every tuple of the S, so we are multiplying the number of tuples. So when we will be selecting with the cross product, we will have the same number.
Perfect. So the idea is that the number of tuples created is both of them multiplied together. Yeah, because we take every pair and we put them together. Okay, so what about the union? So the union, it's tricky because you don't have, there's no specific value, but you can come up with an upper bound and a lower bound. What do you think the upper bound is? Please.
Cardinality of R plus cardinality of S.
Perfect. Yeah, why is that?
It's if they were all unique, there were the duplicates, so all of them are plus all the ones.
Exactly. So if we have R and S two relations and we're unioning them together, it's like the total number of tuples created is total number of R and total number of S. So it's plus. What is the lower bound?
Maximum.
Okay, just one person, please. I didn't hear. Yeah.
Maximum of cardinality of R and S.
Why is that?
Because if all of the, like one is subset of another, then the larger set would be the answer.
Exactly. So if you have R and S and you union them, right? And one of them is the larger one and it contains the other one, right? So it's the maximum of both of them. And that is the lower bound. You will never get something that is less than that. All right, so set difference. What is the upper bound? What is the lower bound? Set difference R minus S. So what is the upper bound? Cardinality of R. Who said that? Okay, so why is this?
If there are no common attribute values in between these two sets, then the final
Return the whole R.
Yeah.
Perfect. So if there are no common attributes between R and S, it will return the whole R as the answer to the set difference, R minus S. And the lower bound is 0. Because if they're both the same, they will cancel each other out. Again, very simple math. And this is exactly what the optimizer is doing. What about the join? So I mentioned something about the selectivity factor of the join in the beginning. But how can we calculate that in a more systematic way? So the join is a special case of the Cartesian product. And the Cartesian product is cardinality of R multiplied by the cardinality of S. This is the total number of tuples they create. So the selectivity factor or the cardinality of the join between two relations is equal to selectivity of factor of the join multiplied by the cardinality of the Cartesian product, right? However, sometimes it's not easy to calculate the selectivity factor of the join. So it is, because I just want to go back. Selectivity factor of the join condition, it's especially if you have a foreign key, primary key relationship, it's not as easy as calculating selectivity factor on the selection condition, because you don't know how many values are represented in between the foreign key and the primary key. And you need the statistics from both relations. So if you have a primary key, you know it's unique for each tuple, so you can calculate it easily. But for the foreign key, this is actually where the trick comes in. Right? So if you know this, you can use the statistics from the foreign key table to calculate this kind of selectivity factor. There's also one thing I want to talk about. So what I was giving you is just I'm giving you an idea of how the optimizer actually decide using the statistics. And I've shown you an example live last time using the Postgres query optimizer. What I recommend that you guys do is that you play with Postgres a little bit and learn more about query optimizer with more complex plans, even for the assignment that you had. So you already had SQL queries involved in the assignment. Just play and see what kind of plans that the optimizer used actually for this. Speaking of the assignment, how many of you thought the assignment was complicated? That's good. Yeah. So I'm not going to ask the opposite question, right? But this is good enough. Again, in that discussion forum, we have a total of about 100, not exactly, but about 120 posts. So, which is okay, but I mean, some of the posts are repeated, some of them, not all, questions of other questions, right? So try to look at other students' posts, please. And maybe if you have a follow-up question on the same post, add it to the same thread. It would be more efficient that way. So 120 posts, I think it's a lot, but I mean, we cannot, sometimes it cannot be humanly possible to track all of this, right? So, but we try to respond. And again, look at other people's posts and ask questions early on, right, instead of later. Because again, you might have noticed that we had a flurry of posts in the last few hours before the deadline, right? So it's hard to follow up with these, right? So try to ask the questions early on. So how was your experience with the virtual machine? Was it a good experience? Yeah. Okay, you don't like it. It's not what?
In Mac, you cannot use virtual machines.
You cannot use.
Windows and Linux Xbox.
I have a Mac and I use virtual machines. Yeah. It depends. There are different softwares to be able to run virtual machines. So, no, it should be fine. You should look more into that issue. No, I mean, here's the thing. The concept, I want to say something. The concept of using virtual machines, folks, the concept of using this virtual machine and sending you this image is to give you an idea of how this will be graded. And also to make sure, in the past, we used to get a lot of questions about what version of Python, what version of Postgres, what version, it's like all these kind of questions, and can I use this version? So this is why we give you an image. We tell you anything that will run with this image, it will be fine with us, right? So this way you can easily, instead of, we minimize this kind of conversation between you and us. So we make it easier. With every single assignment, we're going to be doing that. So because this is facilitate things. However, sometimes you might find issues. We understand that. Please report the issues early on, and we'll be happy to take it into consideration. For the project, how many of you started with Apache Spark? Played with Apache Spark a little bit? Okay. No one. Like a few. Okay. For the people who, first of all, people who didn't start and didn't raise their hands, thanks for your honesty, right? I admire it. But, so that's a good thing, okay? So the bad thing is that if you don't start as soon as possible, when the time comes for delivering, it will take you a long time. So this is part of the process, asking you to start to learn about Apache Spark is part of the process. It's not just a luxury, okay? So this is why I recommend that you guys do it. And if you don't do it, the first phase of the project will actually force you to do that. Anyway, but you won't have enough time if you don't start playing with it. We're gonna have you guys. Have we posted the project phase 1 or not yet? No. We're gonna post it this week, right? And what I'm gonna ask you to do is something. I just want to. In the project, the first phase is basically you're not gonna implement anything new, but you're gonna run existing libraries and software that runs against Apache Spark. Okay? So we're gonna ask you to report the results. So it's just running and reporting results. Very easy. It's if you don't score well on this phase, there's something wrong. Okay? So I'm telling you. So this is a phase to collect marks. So, but it requires work. It's not just a piece of cake. And we actually, in the first phase, we're not going to give you any instructions on how to use the system. We're going to give you some instructions for sure, but we're not going to give you instructions of how to set up an Apache Spark cluster. We're not going to give you instructions about like the things that the IT things, right, that people usually do when you install a new program or anything like this. Why is that? Because we want you to go through this learning experience. But after the first phase, we're going to provide you with the same virtual machine that you had for the assignment. We're going to provide you with a virtual cluster. The cluster will have between 10 and 20 machines in it, and it will have like a lot of like more than whatever than your laptops, for instance, or something like that. It'll be like a real cluster you can play with, and this cluster will be a replica among all the groups, and everything is set up, and all the libraries are there, and everything is just you need to run your code or write the code and run it. And this will be for phase 2 and 3, where you need to actually develop something. But we wanted you again to go through the process of, because this process is painful, right? And I want you to feel the pain, right? Because again, if you're going to work in the future in a company or something like this, you need to know how to download stuff and work with it. And I'm assuming you guys have done that before, right? But this will give you an experience how to set up a Spark cluster, a Hadoop cluster, all these kind of things. If you don't feel that pain, you're not going to learn, right? So phase 1 will be posted this week. And you will have like a couple of weeks to finish phase 1. And from now, and from then, we're going to have phase 2, phase 3, also a couple of weeks, right? Till we reach the end of the semester. All right, so this is just FYI. Okay, so far, the optimizer that I've shown you is, okay, enough. So the optimizer that I've shown you, it optimizes based on the I/O cost, which is the number of I/O operations. But in a parallel database system, in a system when you have multiple components running, it may not be the case. Why is that? So transmission time may be may dominate in this case, because you need to do some processing on one site, and some data on this site needs to be transmitted to the other site to continue the processing on this site. It's necessary to answer the query to transmit data between sites. So in this case, I/O cost alone is not enough. Not only this, again, parallelism makes a difference. So if you have site 1, you have 100, even if you take an I/O, so if you have a parallel system, this I/O cost model that we've shown may not work, because plan A takes like this amount of I/Os, while in fact, if you have multiple sites, you have more number of I/Os than 100 I/Os. This is more than 100, the combination of these I/Os. But the query will finish faster, because the maximum among them is 70. So in this case, even though you have more I/O operations in the parallel system, because the query running across multiple machines, this plan might be better because it finishes fast. You guys understand the point? Okay. So in this case, a cost model that just aggregates the number of I/O operations may not be the best way, like the best cost model for the query optimizer to pick the best plan. So in this case, the query optimizer needs to take into account, first of all, the number of machines that run and the I/O on each machine, and then it needs to have like maybe choose the maximum across all of them. And if you have different distribution of the data across multiple machines, you might have different statistics across across these machines, and including also the communication cost. So it becomes more complicated that way. So sometimes, like, you may think about separating the query into 2 or more queries, because if the problem is if the query is very complex, one global query optimizer may not be good option, because the problem might be so difficult for this global optimizer. So maybe you need to separate the queries into simple queries and optimize each of the steps in the query independently. So in this case, so you have a selection here, selection on R, selection on S, and then a join, and then a selection on the join. In this case, you might actually push some operations down like this, because since the only thing you're interested in the join is basically the join on the attribute A. Joining an attribute A requires only the values in the A attribute. So one way is to instead of getting all R and S passed into the join operation, you just pass R and S but projected on the attribute A. And the reason behind this in a distributed system might be minimizing the communication cost. So you want to minimize the amount of data transmitted. So you do the join only based on the attribute A, and then you reconstruct the relation if necessary. So something like that. So you compute the R prime and S prime, and then you compute the join, which is just a join based on the A value, and then you can compute the final condition based on the reconstructed kind of attribute. So the idea is that this plan may not be in a centralized system, may not be efficient, but in a distributed system, depends on where the data is. This kind of join, semi-join that you did, might be very useful to minimize the amount of data transferred across the network. Depends on where the data is. So you compute A values in the answer, and they get tuples from the site. So this is basically the main idea behind this. So this simple query idea is basically, even though you don't get the most optimal plan in the universe, but again, it's a very useful idea, especially when you have a distributed system, as we mentioned. And a lot of the distributed database systems, they use this very simple idea to optimize the data transfer across the network. And remember why we do it specifically for the join, because join is a complex operation and requires, sometimes you need a global view of the whole data to join the 2 tables together, as opposed to selection or projection. So this means if you have tons of machines and you have data distributed across these multiple machines, you might there is the possibility of having data shuffled across the network is way higher with the join. So this is why using this very simple trick can help minimize this amount of data transfer. All right, so yes, this is basically, I will just end it here when it comes to the simple queries and how to run joins, distributed joins in general. So, so the project. I want to talk a little bit about the project. I talked briefly about it now, and I talked briefly about it earlier in the semester. So the project basically will ask you, all of you, each group, to build a SQL system on top of Spark. So there is, Spark is basically a big data processing engine. It allows you to write code that processes data, and it automatically parallelizes the processing of this code in a cluster. And this cluster is a cluster of multiple nodes, multiple machines. These machines can be in the scale, depends on the needs that you have in your system, but so many of the Spark system can scale to hundreds or like even thousands of machines in the cluster. So if you have a huge cluster, like at ASU we have many clusters to run big data jobs. You can actually set up the cluster so that Apache Spark takes on the processing of the data on this cluster. Right? So what kind of, when I say big data processing, what is it? What do I mean? So the data can be stored in any data source. The data source can be a database, like Postgres for instance, or it can be a file system, a regular file system or Hadoop file system, a distributed file system. And basically you provide the data source to Apache Spark. Apache Spark loads the data from this data source into the memory of the Spark cluster. This memory definitely is distributed across, because you have many machines running in the system. So each machine has its own memory. You get part of the data and you load it in this memory of this machine. If you have 1,000 machines, each has 1 gigabyte, you can have 1,000 gigabyte, right? So 1 terabyte. For instance, giving you an example. And once you load it, Apache Spark gives you abstractions that helps you write programs. This program is like it's as if you're writing a Java program that processes this data. You can say, load the data, filter the data, integrate the data with other source. Any kind of logic you have, you want to run on this data, it allows you to a simple abstraction, programming abstraction that helps you write this. So you write your program, you load it in the cluster, the same exact piece of software runs across all the machines, and hence you get like a massive parallelization of this job across multiple machines. And the result, you can either pipeline it to the user, or you can store it also in the same data store that you have, or a different data store. The results of the job that you ran. Okay, so there are different libraries running with Apache Spark. One of the libraries is a SQL library. So the SQL library assumes that the data is, again, it's a relational data. So you have tables, and you have rows in the tables, and you want to do a join, for instance, on these two huge tables. So it's a data processing operation, but it's a relational data processing operation. Okay. So Apache Spark, there is a library that runs on top of Apache Spark that allows you to do that. It's called Spark SQL. And it allows you to do more than that, like SQL operations. So what you're going to do is you are going to implement operations that can process geospatial data in Apache in the Spark SQL. Which means if you have data that has geospatial attributes, like geotag tweets, you have tweets that has a geotag attached to it, and you want to process this data. You want to filter it, you want to aggregate it, you want to do multiple things on it. Okay? This is a geospatial data you need to deal with. Or if you have data coming from sensors across the city. Okay? This also considered geospatial data. Okay? If you have data coming from, you have taxi trips, and you have billions of records of taxi trips, and you want to aggregate them and get this aggregation and visualize it on a map. So this aggregation is basically a SQL query. It's a group by query by the region, and it might have a join as well in it. So this is also kind of an application. You might use the system that you guys are going to build. So we're going to define about like 5 operations you need to support in the system. And to make you understand what kind of operations we want you to do, we're going to ask you in the first phase to run these operations in a system that we already built called GeoSpark. But this GeoSpark system is not a SQL system. It's just a basic, it runs with the native Spark system. The same operations of GeoSpark that you're going to run and test in the first phase, you're going to implement them as user-defined functions in Spark SQL. And this will be like phase 2 and 3. What are these operations briefly? These operations are basically if you have a set of geospatial points in the space, like again, locations of the taxi trips on the map. These are billions of these. You want to filter them based on a rectangular range, or you want to filter them based on the zip code, specific zip code. You want to return all taxi trips that are in this zip code, that are picked up in this zip code area. This is called the geospatial selection operation, geospatial filtering operation. That's the example. Another example is you have 2 data sets. One is this taxi trips, and the other one is weather data. And they all have like a geospatial component. So the weather, the taxi trips in Phoenix, and the weather data when, like forever, what's the name of the storm that happens here? The big one? Haboob, right?
Harvey.
What is it? No, storm that happens here. Not here. It's called the Haboob, right? Yeah. So we can actually, if you want to join to find the number of taxi trips that have, like how many taxi trips are being taken while there is this kind of sandstorm in the city, in the Phoenix area. So this is a spatial join operation, okay? We're going to ask you also to implement something like that. So I'm just giving you an idea of what kind of operations you're going to do. So there is a system that does that already. What you're going to do is that you're going to mimic this system, but into SQL. Again, this is not an easy thing to do because the current version of GeoSpark work with a different data model in Apache Spark. You're going to work with something called a data frame in Apache Spark. And the data frame is like something like the table, right? So this is different. So this is why I want you, every single one of you, to look at Apache Spark, look at Spark SQL, and the first phase of the project, again, is going to force you to deal with GeoSpark, run operations with GeoSpark. I'm not sure why you're getting ready to leave, but still 5 minutes, something like that. So you don't want to listen about the project. I mean, I'm going to minimize the talk about it, right? So, okay. I promise I'm not going to talk much about it. I'm going to post phase 1 instructions this week, and you're on your own, okay? I'm not going to talk about it at all, okay? You're expecting me to stay after you give me the signal that you want to leave, right? Okay, it's fine. Class is dismissed. You guys can leave.